Now, small blood vessels. This is a completely separate issue from osmolar draw. Completely separate. Arteriolar constriction and dilation has to do entirely with hydrostatic forces, pressure of water, not osmolar pressure. In the kidney, we filter about 20% of glomerular filtration rate is about 20%. The filtration fraction. We put about 600 mLs into the kidney in renal plasma volume, and about 120 mLs come out as glomerular filtration rate. Even though we filter 20% of the kidney, the pressures between the afferent and efferent arterioles stay the same. How can you have the same hydrostatic pressure at the beginning and the end of the afferent arteriole if you just filtered 20% of it? How can you have the hydrostatic pressure be the same if you've lost volume? Constriction of the arterioles. The constriction and dilation of arterioles maintains hydrostatic pressure constant. And you need constant hydrostatic pressure to have a stable biological system. So hydrostatic pressures are maintained by the dilation and constriction of various arterioles. And you notice not venules. Not venules. Why not dilation and constriction of venules? Because veins don't have circular muscular layers around them to dilate and constrict. Arterioles do. Venules don't have circular muscles around them, but arterioles do. When you open up an arteriole, it's the same as turning on the faucet in the bathroom or the kitchen. You're increasing the flow. You dilate the arteriole, more flow in there. If the artery stays the same and you increase the flow, the artery diameter stays the same and you increase the flow, what happens to the pressure? The diameter later on stays the same, but I increase the flow into it. What happens to the pressure? Will it go up or down? I increase the flow into the same size artery later on, it increases the pressure. More volume, same size later on, more pressure. That's how we control hydrostatic pressures, by increasing and decreasing, by dilating and constricting arterioles, not venules. Also, large arteries can't constrict and dilate. The aorta doesn't constrict and dilate. It's too big. The same way, on major highways that have 4 and 6 lanes, they don't have stoplights. Stoplights is for small roads. Big highways don't have stoplights because you can't control flow that way. The big highway is like a big artery, huge artery, an aorta, a femoral, a brachial. You don't constrict and contract. You don't constrict and dilate the femoral artery. You constrict and contract teeny arterioles, just like small roads have stoplights to control flow, not major highways. Same idea. As a matter of fact, an artery like the aorta, if you live at the size of 5 microns, which is the size of a red blood cell, a large artery like the aorta is the equivalent of transcontinental flight, about 600 to 800 miles an hour, 600 miles an hour. A modest-sized artery is about 300 miles, 250 miles an hour. And small arteries is like driving your car at 120 miles an hour. So that's the relative velocities. It's only when you get down into small arterioles it becomes a normal-sized highway, 55, so to speak. So there's no resistance between the capillaries and veins because capillaries don't have muscular layers in them. Arterioles do. So when we talk about afterload, we really mean arteriolar resistance, the smallest arteries before you get to the capillaries, but not between capillaries and veins. So if you think about it, large arteries don't constrict and dilate, capillaries don't constrict and dilate, veins don't constrict and dilate. Small arteries, arterioles, they constrict and dilate. But because of the back pressure, they do control the pressure all the way back up into the left ventricle. If you constricted every one of these arterioles out here, you can control the back pressure into the heart. But arterioles would change. Capillaries are highly permeable, and they're permeable because they're not surrounded by a muscular layer that can dilate and constrict. I got some good news and some bad news. The bad news is that the capillaries don't dilate and constrict. There's no muscular layer to control flow. The good news is that things can diffuse in and out because they're very thin. They're too thin to have a muscular layer, but they're thin enough that things can diffuse across them. That's the point. They're so thin that proteins can leak out into the interstitium because capillaries are very thin. It's like little side streets outside the building. You don't stop your car on the side of a huge major highway. You got to get off the highway. But you can stop your car on the street where you live to get in and out of your car. The lymphatic system there picks up proteins that are removed because lymphatics are very, very loose. The walls of lymphatics are so loose that proteins can get into them. Now, this thing here on the next slide can look seemingly complex, and when you put numbers in it, it will feel complex. But the idea of it is not complex because, in fact, the idea of it is what I just said, hydrostatic pressure. The idea of it's very easy, and the good news is it's just addition and subtraction, no multiplication, no division. So it's the kind of mathematics that medical students can handle. Now, the most important forces here are hydrostatic pressure, not osmolar, hydrostatic. Hydrostatic, like a water hose, like a garden hose, like a fire hose. Hydrostatic, like sucking up stuff with a straw. And oncotic. Now, oncotic could be a misnomer because we have oncology, which is the study of cancer, has nothing to do with it. And we have oncotic in here, where oncotic here means protein. So why don't we just say oncotic equals protein and life will be good. Now, this symbol that looks like pi is the same thing as saying oncotic. The major thing here, your mantra for today, is hydrostatic pressure. Om Namah hydrostatic pressure. Om Namah hydrostatic pressure. Om Namah hydrostatic pressure. Satyamev Jayate. Truth shall prevail. Hydrostatic pressure, here it is. The forces that go in and the forces that go out. The forces for filtration. The forces for filtration is the hydrostatic pressure that's in the capillary. The hydrostatic pressure is in the capillary plus the oncotic pressure that is in the interstitial fluid. Okay, for filtration is the push out of the artery or arterial and the pull out. It's the push out of the artery and the pull out. Hydrostatic pressures in the arterial push fluid out of the arterial. Oncotic pressure in the interstitial fluid pulls the fluid out of the capillary. That's the forces for filtration. And the forces against filtration, also known as forces of reabsorption, the forces against filtration would be the hydrostatic pressure in the interstitial fluid plus the oncotic pressure in the capillary, because the forces against filtration are the hydrostatic pressure in the interstitial fluid, which pushes the fluid back in, and the oncotic pressure in the capillary, which pulls this in. Okay? Cannot review what you never knew. If you took physiology in college, you'll think that this is very easy and you're done. Just fast forward. If you didn't take physiology in college, or you fell asleep during that class in medical school, and you'll think, the good news is it's not going to change. You know, it's not going to change. Also, the other thing is this. Don't try and do the nephrology section without understanding this, okay? Because you're not going to understand it without understanding these two things. This is the very basis upon glomerular filtration rate. The very basis upon glomerular filtration rate is understanding that oncotic pressures and hydrostatic pressures between the both of these control how much fluid is filtered. In the kidney, what happens to hydrostatic pressure between the beginning and the end of the arteriole? Let's say that we have an afferent arteriole, which is a $5 word for to, and an efferent arteriole, which is a $5 word for from. Hey man, I'm not getting $200,000 in debt to say to and from. I'm getting $200,000 in debt to say afferent and efferent. You filter 20%. What happens to the hydrostatic pressure between the beginning and the end of that capillary? The answer is nothing. How can you lose 20% of the volume but have no change in the Om-Nama hydrostatic pressure? Om-Nama hydrostatic pressure. And the answer is constriction and dilation of these arterioles. That's how. You have constriction and dilation of the afferent and efferent arteriole to maintain constancy. Constancy. Not until the sun excludes you do I exclude you. Not until the waters refuse to glisten for you and the leaves refuse to rustle for you shall my words refuse to glisten and rustle for you. Constancy. For she is wise, if I can judge of her. And fair she is, if mine eyes be true. And true she is, as she has proven herself. Therefore, like herself, fair, wise, and true, shall she be placed in my constant soul. That's the Merchant of Venice, right? Merchant of Venice, right? Merchant of Venice. So that's it, constancy between the beginning and the end. Om-Nama hydrostatic pressure. So let's look at the formula! No! Oh, that was scary. There's a formula on the next slide. I can't do it. It's a formula. Because I think we were just about to understand it, and there's a formula. There's a scary formula. Man, there's like Saw 5. Saw 5, episode 5. The calculations and the equations. It's like House of the Dead. Yeah. House of the Dead. Okay? Equations jumping out at me. I don't want. Equation. Filtration. No, too much. I can't. No, forget it. Filtration coefficient. Get rid of that. That's too much for me. Fluid movement. Why do I have to call it Q, man? Q equals flow, okay? Q equals flow. All right, it is. And Q of the F means flow of the fluid. Why can't we just say that? You know what I mean? Why can't we just say flow? Why do we have to say FQ? I don't know. That's what I think about this FQ. All right, so the thing is that the flow of the fluid, if you're getting scared by this formula, is what I just said. It just said, well, let's go back. The forces for filtration is the hydrostatic pressure in the capillary, pushes it out. The oncotic pressure in the interstitial fluid pulls it out. Oh, look at that! It's the hydrostatic pressure in the capillary, and the oncotic pressure is the forces for filtration. minus the forces against filtration. And that's just a net. That's it. That's the point. The point is, this formula is what I just said before. Hydrostatic pressure in the capillary pushes fluid out. Oncotic pressure in the interstitial fluid pulls fluid out. And the hydrostatic pressure outside the capillary is pushing back in. And the oncotic pressure in the capillary is keeping the fluid in. And you're just taking the forces for and the forces against filtration, and that will give you the rate of flow, the force of flow for the fluid. And this concept you got. So ready? Just keep looking at the formula for a second. It'll be like desensitization, okay? Just desensitize yourself against this formula and it'll be over, okay? Oh no, I can't. Yes, you can. No, no. Just look at it for a while. This is cognitive behavioral therapy. You don't have to like it. Just pretend like you like it, and eventually you will like it. Now, this next slide simply gives you a sample calculation. It says, can you look at some numbers and calculate out a net filtration flow? And this means that you basically have to take the forces here that are for filtration, and say basically the forces that are for filtration, which is the hydrostatic pressure in the capillary and the oncotic pressure that is in the interstitial fluid, which is 26, is for filtration, and subtract out what is the hydrostatic pressure within the interstitial fluid and the oncotic pressure in the capillary, and say 22, and say 26 minus 22 equals 4. And it says basically you have to just go through the calculation and be able to say, what are the forces for? The forces for is the hydrostatic pressure in the capillary, and the oncotic pressure in the interstitial fluid is 4 minus the other two, 26 minus 22. Now that's why the first one is 4. Now here it says, well, now switch it. It may not be terribly clear from the slide, and it basically says switch it so that the interstitial hydrostatic pressure is now minus 2. Switch it so the interstitial hydrostatic pressure is minus 2. So that means that this one over here, that hydrostatic pressure that was 2, change it to minus 2. That's why it changes, okay? So this next one, we erase all the other calculations. We do change this to minus 2. Change this to the interstitial hydrostatic pressure is minus 2. So now we have the forces favoring filtration is still 26, and the forces against filtration, let's see. Oh my goodness, minus 2 plus minus 2 plus 20. Minus 2 plus 20, how do you add minus 2 plus 20? Minus 2 plus 20 is 18. So now we changed it from 26 minus 22 to 26 minus 18, and that's how we get the 8 difference. And this is just an example of saying what happens when you alter those pressures. In both of these cases, the net result for filtration is that they'll both end up in filtration of fluid out of the vascular space. It's just that one of them gives a smaller amount of force of filtration, and the other one gives a larger amount of force of filtration. It's basically saying that as you decrease the hydrostatic pressure in the interstitial space, as you decrease the hydrostatic pressure in the interstitial space, you will increase the forces of filtration. In other words, the hydrostatic pressure in the interstitial fluid is opposing filtration. As you decrease the hydrostatic pressure in the interstitial fluid, you're making it easier for things to filter out. And that's all it's saying. The lower the hydrostatic pressure in the interstitial space, the greater the forces of filtration. Now, the concept of this next point is an easy concept. Like most things from medical students, you can take an easy concept that you understand, put it in a formula, and make you want to commit suicide. The concentration concept, which is that you have this amount of substance, and how much do you dilute it into? How much volume? This amount of substance put into a changing volume changes the concentration, is not difficult Because it's the concept of I put one sugar into a small coffee or I put one sugar into a large coffee and it changes the concentration. The concept is not a hard concept because it's called I put a small amount of sugar into a big coffee, into a small coffee, or I put 5 sugars into a small coffee is a greater concentration than 5 sugars into a huge coffee. The concept is not hard. Putting it in a formula is irritating. So this basically says if you want to look at the volume of a compartment, you inject a tracer and see how much it disseminates or diffuses around. This is how you calculate volumes of distribution. You take a tracer. The tracer, in order to see a total body water, has to be something that goes through all biological membranes. So how is it that we know this fact that 60% of me is water? Well, how do we figure that out? Well, because we inject a certain amount of tracer and see how much it disseminates out to. We take a certain amount of tracer, inject it into me, and see what is the ultimate concentration. So what we know is that the concept of injecting a tracer and looking at the change in the concentration is a way of telling the total volume. No one has a problem with the concept. The problem people have is the formula. We use things, that's why we say tritiated water. Tritiated water is basically something that diffuses everywhere. That's the total body water. It's a tagged water, that's all. Tritiated water, tagged water. That's all. And disseminates everywhere. So if we want to say, look, the volume of the compartment. Oh, look at these formulas. What a pain in the butt. The volume of the compartment says that, how do we tell the volume? This is the total volume of the compartment. So we injected a certain amount. We injected a certain amount of the tracer. And we said, well, what did it disseminate out to in terms of concentration? And that's all. It's saying, look, I put 1 sugar into a certain cup of coffee and it came out to this concentration. Or I put this sugar into this bigger cup of coffee and it came out to a different concentration. So I figure out what the volume of my cup of coffee is by calculating out the amount of sugar in the cup of coffee. I put 1 sugar in an espresso, it has a high concentration. I put 1 sugar in a 55-gallon drum, it has a lower concentration. The concept is all that matters. That's really all that matters. So just when you're about to, like I said, the medical students understand the concept. Watch the formula. I can see that you're about to understand it. I know it's not hard for you. And I could see that you are just about able to understand the concept, yeah. I can see that you are just about able to understand the concept. And even the equation is not so confusing for you. But I cannot have you understanding something. Because if you understand it completely, you will not need me. And what will I do? I'll just be another modestly entertaining bald guy. Well, I can't have you not needing me. I've got to make this as confusing as possible so you feel helpless. So therefore, I can see you're about able to understand the concept of taking a certain amount of a tracer, dividing it by the concentration, and seeing what the ultimate volume of distribution is. So in order to make you confused, I will now give you numbers. And we will put numbers in here and you will have a seizure and rectal prolapse. You cannot understand it. You need me. Welcome to regular medical school. Regular medical school is largely based on proving that I know more than you know. And that's what the whole thing is. You see, the whole idea of this medical school is to eliminate the need for ourselves. You see, my intensity is based on the fact that we're supposed to make it so that you never need to watch me again. I hope that you will never see me again. Why? Because that means you don't need me. And that's a good thing. That's a good thing. Because we don't want you needing me. We want you to understand everything so you never need me again. That's what we want. Like good parenting. We don't want dependent children. We're in the business of raising independent children here, okay? So my father used to say to me, hey kid, we're not in the business of having dependent sycophants here. We are in the business of raising independent adults. That's what my father used to say to me. Now get out, all right? So if we put in 300 milligrams of a dye and it gets injected, blah, 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 at equilibrium, bullshit, bullshit, okay? And now we have a particular concentration. So let's go back to our particular formula, okay? Let's look at our formula. Okay, we put a concentration of a particular dye, 300 milligrams of a dye, and we want to figure out what the total volume is. So we put in a particular amount of a dye into a tracer, and we find that the concentration was, well, 0.05. Well, what does it mean that if we put in 300 milligrams and you only have 0.05 milligrams of concentration, it means it had to be distributed amongst 6,000. Because 0.05 is the same thing as saying 1/20th. It means that I put in 300 milligrams. The concentration at the end is 0.05. So what ended up happening in here is it got distributed down to a concentration of basically diluted 1/20th. So that means, let's see, if the concentration inside there was, let's say it was 1. Let's see, the concentration, if we put 300 milligrams in there and the concentration was 1, that would mean the volume was 300 mLs. If we put 300 milligrams in there and the concentration was 0.1, then it would be 3,000 milliliters. If the concentration comes out to 0.5, so that means it's half the concentration, twice the volume. Let's try that again. If we put in 300 milligrams and it came out to be a concentration of 1 inside there, that would mean that it was distributed amongst 300 mLs. If the concentration was 0.1, it would be distributed amongst 3,000 mLs. If the concentration is half of that, it's twice the amount of volume. The concept is not hard. It's just the calculation's a pain in the ass. The volume of distribution is simply how much did you put in there and what was the ultimate concentration. And you divide the amount of the tracer by the concentration and you get the volume of distribution. And that's all. Now, tracers, remember that plasma, okay, plasma proteins, not permeable to capillary membranes, that's saying, yo, big proteins, can't make it out of the capillary, big protein can't make it out of the capillary. I put an 18-wheel tractor trailer down a side street, it should not make it into your living room. Oh yeah, I put a minivan or an SUV in your sidewalk, it shouldn't make it through your front door. Yeah, it's like too big to get in there. It's got to stay in the capillary. So, I can't use plasma proteins to discriminate volume and distribution because it will only tell me what's in the vascular space. It doesn't diffuse because it's too big to get out. Plasma proteins are too big to use unless I want just to tell me the vascular volume. If all I want is vascular volume, use a plasma protein. And we do that. We have tagged albumin. You can use tagged albumin, and tagged albumin will stay in the vascular space. But it won't tell you the volume of distribution of water. It'll tell you the vascular space only. Oh, how is it that we did determine plasma volume? Tag the albumin, baby, and then you'll know the vascular volume. Period. Nothing about the extracellular fluid except the vascular volume. Won't tell you about interstitial. Now, let's say that I wanted to measure the total extracellular fluid volume. I'd have to use a tracer that could be through the capillaries, pass out of the capillaries, but not go into cell membranes. I'd need something that was not particularly reabsorbed and not filtered at the glomerulus. And an example of that is inulin. Not insulin, but inulin. Now, inulin is something that doesn't exist in the human body normally. It's a derivative, believe it or not, of the Jerusalem artichoke. It's a tuber, it's a root. It's a root extract, but we can use it because it's excellent because it doesn't go across cell membranes. It's filtered, but doesn't get reabsorbed and doesn't get secreted. It goes from the plasma volume, but doesn't go into cells. Inulin is a good example of that. Last one, total body water. Total body water would have to something that penetrates all biological membranes, but not fat cells. Total body water, but not fat cells. And a good example of that is urea. Urea will go through urea or tritiated water. Urea and tritiated water basically will go into all cells that have water, but not in the fat cells. Now, there's blood volume, plasma volume, again, is a concept that you understand as a concept. Once we put in a formula, you go crazy. It basically says this, that in order to get a certain amount of plasma volume, let's say that we want 600 mLs of plasma in the kidney. Well, in order to get 600 plasma, which is the juice, we have to put much more blood than that to get that amount of juice. So if we want 600 mLs, we can't put 600 mLs of blood in there because the blood is only partially plasma. The blood has red cells in it. The blood has red cells. So in order to get this amount of plasma, of juice, we have to put more blood to get that amount of juice. And this formula basically says that the higher the hematocrit, the greater the amount of blood you have to put in to get that juice. The lower the hematocrit, the less the amount of blood you have to put in to get that amount of juice. If you have a very thin blood, hematocrit at 10%, well, blood volume and plasma volume are practically the same. If you have a very high hematocrit, like polycythemia vera, you have to put much more blood to get the same amount of plasma volume because the blood ends up being very thick. Now, this is very important in filtration things like the kidney. You see, only plasma filters. So if you want to clean out your blood at the kidney and you want to get a lot of plasma volume to clean it out, if you have a very high hematocrit, you have to have more blood going through that kidney. A low hematocrit, less amount of blood. See, plasma is what filters at the kidney, not the red cells. So this formula is saying that the higher the hematocrit, the more amount of blood you have to put in to get the same plasma volume. The lower the hematocrit, the lower the amount of blood. Now, remember, hematocrits, although you think of them as percentages, a hematocrit of 50% has to be put as a decimal. That's what tortures people. A hematocrit of 50% means that it's 1/2, 0.5 plasma. And that's why you're basically taking the 1 minus 0.5 because you have to put it in decimals to understand it. That's what's saying that if you want 3 liters of plasma, you got to get 6 liters of blood in there if the hematocrit is 50%. If the hematocrit was 10%, if the hematocrit was only 10%, 1 minus 0.1, wow. 1 minus 0.1, wow. That means, 3 over 0.9. That would mean that you would only have to put 3.3 liters in there. So that means if you drop the hematocrit, as you drop the hematocrit, you only have to put a tiny bit more blood in there than the plasma you need. The lower the hematocrit, the greater the amount of plasma. The higher the hematocrit, the less the amount of plasma. The concept is not hard. The calculation is irritating. Okay. Now, what maintains or looks at just the vascular content? Whole blood. First of all, we never use whole blood therapeutically anymore. Whole blood is red cells and the plasma. Whole blood is red cells and the plasma. Therapeutically, we never use whole blood. Whole blood hasn't been used in 30 years. Is that we use either fresh frozen plasma or we use packed cells or we use platelets or we use clotting factors. We never use whole blood, but it is something that's just in the vascular component. Now, whole blood or the portion of it that's plasma, and remember, plasma means proteins, and since it's proteins, they don't go outside the vascular space because they're too big. Capillaries may be able to diffuse things across them, but they don't diffuse albumin across them. They don't diffuse big proteins. Dextran is a sugar, a large sugar. It's a volume expander. We used to use it therapeutically. It used to be used in big trauma as a volume expander. We don't use it much anymore. Dextran was a nifty idea because we have all been looking for blood substitutes for 100 years. However, generally speaking, when people come into the hospital, we just give them blood. Every time we used to think we'd use Dextran because it would expand the volume of the intravascular space, well, we pretty much just use blood. If I was in a place where I had no blood to give, I might use Dextran, because Dextran means a large molecule that stays in the vascular space. It's a volume of vascular space expander, Dextran. Now, saline and mannitol will look at the whole extracellular fluid because they will pass across membranes. They will pass across membranes and will go into the interstitial space. They will go into that interstitial space. So the total body water is basically, we give it as 5% dextrose because we don't want to give hypotonic solutions right away, because if it's just water, the cells will hemolyze. So we give 5% water so that the cells don't hemolyze, but once the dextrose goes away, the water will disseminate evenly throughout all the water-containing compartments of the body. Now this next slide, in different words, says the same principle. And one of the hardest things about preparing for a test like this in basic science is that it can take something you already understand, change the words, and you'll stand there and look like this. What's that? So it's the same thing you already understand, and we change the words. In vitro solution, due to the movement of water across cell membrane osmosis, well, this is saying what we said before about osmolar concentration, that we change the osmolality of a particular fluid, and it changes the osmotic draw of water across cells. Now, effective osmolality means that you infuse something where the osmoles don't go in across the membrane. They don't go across the membrane. You see, if I infused something that had osmoles, and those osmoles instantly distributed evenly everywhere, there would be no osmotic pressure. There would be no net movement of fluids. If I put something into you that essentially the osmoles instantly diffused, intracellular, extracellular, there would be no net movement of fluid. Effective osmolality means that the solutes stay in the space you put them. I put those solutes just into the plasma. The solutes, the osmoles stayed in the plasma, and they take fluid out of the cells. That's what it means by effective osmolality. Effective osmolality means not diffusing, not evenly distributing osmoles or solutes. The osmoles stay where you put them, and they create an osmotic draw for the water. Now, this last one is just a repetition of what we said before, which is that water will diffuse from a region of higher water concentration to a region of lower water concentration. Now, like in this little itsy-bitsy tiny drawing here, the instant drawing, effective osmolality means that those osmoles did not evenly distribute between both compartments. It stayed in one compartment. Because they stayed in one compartment, water diffuses from the area of high water concentration, which is to say dilute, to the area of lower water concentration, which is to say concentrated. Now you notice that before we said concentrated and dilute, and now we change it to higher water concentration, lower water concentration. Yeah. Just to torture you. Just to hurt you, slap you around. Slap around your frontal lobes. Pink, 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 pink. High water concentration means low osmolality. Low water concentration means a high osmolality. Effective osmoles means that they don't diffuse instantly. They stay where you put them. Isotonic saline has no change in red cell volume because it has the same osmolality as what's inside the cell. So there's no fluid movement. There's no fluid movement. The effective osmolality is because it stays the same as what's inside the cell. No net fluid movement. Now, if you give a substance that penetrates cell membranes right away, like urea, this also has no effect on water movement, because if you give somebody urea and it instantly diffuses across cell membranes, it doesn't change the osmolality inside the cells. If you give urea and it disseminates everywhere, it doesn't change any draw because it changes the osmolality equally. Since urea changes the osmolality equally, there's no net movement of water. There are other substances like mannitol that when you put them into a body, what happens is that mannitol will initially create an increased osmolality in one component. And initially there can be a fluid draw into that compartment that gets something like mannitol. Now over time the mannitol will diffuse and become evenly distributed. Initially it acts as an osmotic draw, but over time when the mannitol slowly diffuses around, it ends up being no osmolar draw because it has an equal concentration and it doesn't drive you. You know what it's like? It's like putting on a lot of perfume right away. Initially, I'm drawn. But then after a while, when it diffuses all over me and all over you and are both equally covered with your perfume, it's not going to draw me anymore because now I smell like you. I don't sense it anymore. It's like putting on too much perfume right away. Initially, it's a tremendous draw. After a while, Edema. Edema is caused predominantly by an increase in the hydrostatic pressure within a capillary. When you have an increase in the hydrostatic pressure within a capillary, it pushes fluid into the interstitial space, and that's edema. Those forces which we described before when we said the forces for and against filtration are also known as Starling forces, after a guy named Starling. And it basically says when you think of hydrostatic pressure in the capillary or in the interstitial space and the forces for and against filtration, that's the same thing as saying Starling forces, after our dude Starling. Now, the increase in the hydrostatic pressure in the capillary makes it move from the vascular component and into the interstitium. Now, all edema does not require there to be retention of sodium and water by the kidney. You have retention of sodium and water in the kidney in congestive failure. And so when it says that sodium and water are retained by the kidney, that specifically means three circumstances. Patients with congestive failure, where you have a heart that beats like this. And there's no intravascular volume. And the kidney goes crazy. Oh my God, we got no perfusion, oh my God. The afferent arteriole constricts, the juxtaglomerular complex constricts. You start making renin, angiotensin 2. Aldo. Congestive failure, the heart beats like this. The kidney thinks you're going to die of hypotension. Renin, angiotensin, Aldo. That retains sodium and water. So the retention of sodium and water is contributory in cirrhotics, low albumin. Decreased perfusion of the kidney, renin, angiotensin, aldosterone. Nephrotic, no albumin. Albumin's lost in the kidney. The retention of sodium and water in the kidney. Retention of sodium and water in the kidney is essential for edema in cirrhotics, nephrotics, and CEHF, cirrhotic, nephrotic, and CEHF, cirrhotic, nephrotic, and CEHF. Those are the three. If I wrap a tourniquet around your arm and I occlude venous flow, but the artery is preserved, I can get edema. I don't need to have retention of sodium and water by the kidney. If I have a clot in my leg, I have edema in the leg. I don't have to have retention of sodium and water by the kidney. If I had a clot in the leg, I'm obstructing the venous flow. That increases hydrostatic pressure. So just remember, when it says retention of sodium and water by the kidney, that means cirrhotics, nephrotic syndrome, congestive failure, a constrictive pericarditis, something with decreased renal perfusion. That's when there's retention of sodium and water by the kidney. Peripheral edema. This statement here about non-pitting edema after removal of systemic tissue, what that means, that could be a little confusing to you. Removal of systemic tissue means something like, I did an axillary lymph node dissection. I removed the axillary lymph nodes. I caused damage to the lymphatic flow of the arm. I get edema. I did surgery on the leg, surgery in the retroperitoneum. I removed systemic tissue. What that means, I did something where I anatomically altered the normal lymphatic drainage. And that's what it means by lymphedema, non-pitting edema, lymphedema. It means removing, altering, damaging, scarring, destroying, obstructing the normal lymphatic drainage by removing tissue. That's lymphedema in that sense. Now this pitting edema, now you see it, cirrhotic, nephrotic, and CHF, cirrhotic, nephrotic, and CHF. Pulmonary edema. Now the pulmonary capillary system, anything that blocks up the return of fluid to my left atrium. Here is the pulmonary veins returning fluid into my left atrium. And the left atrium drains blood into my left ventricle. And there's kind of a funny shape in left ventricle. And if I have congestive failure, where I'm not getting fluid out of my left ventricle, what's going to happen is the fluid's going to back up. The fluid's going to back up. The fluid's going to back up, and the fluid's going to back up, and the fluid's going to back up. And when you have left ventricular dysfunction, it causes a backup of fluid into the left atrium, and from the left atrium into the pulmonary veins, and from the pulmonary veins into the pulmonary capillary systems. When you have the backup of fluid into the pulmonary capillary system, that increases the hydrostatic pressure in those capillaries, and that's where you get pulmonary edema. Pulmonary edema basically means this. Your left ventricle sucks. It doesn't pump forward. Since it's not pumping forward, the blood's going backwards. And when it goes backwards, left ventricle to left atrium to pulmonary veins to pulmonary capillaries, hydrostatic pressure goes up in the pulmonary capillaries. Om Namah hydrostatic pressure. Om Namah hydrostatic pressure. Pulmonary edema. Pulmonary edema. Now, when it says second compartment, it means the space between the alveolus and the capillary. There's an extra compartment called the interstitial space, which is actually much larger than anywhere else in the body and builds up fluids. It's an extra space. The alveolus must remain empty. Empty. The alveolar space normally is empty. The alveolar space is normally empty, and fluid builds up in the alveolar space, which is normally completely empty, and the interstitial space in the lungs has a lot more distensibility than otherwhere in the body. You see, interstitial space here in my arm, those cells are very close. There's not much room in between them. But in the alveolus should be completely empty, and the interstitial space in the lungs can really expand a lot. It's soft, it's mushy, it's compliant. So when you have the left ventricle not working and the blood's building up backwards, the hydrostatic pressure in the pulmonary capillaries puts the fluid in the interstitial space and then in the alveoli. Normally the alveoli should be completely empty, and the interstitial space in the lungs is a lot bigger than other places. So you get the fluid in those two extra areas. In order to keep those alveoli empty of liquid, we have to make sure that, one, no protein gets in there. Protein gets in the alveolus, you're totally screwed. Now you got oncotic pressure going into the alveolus. You're in deep poo-poo. So it has to be very tight. Keep the protein out of the alveoli. So there's no oncotic pressure pulling into the alveoli. So the epithelium is completely impermeable to protein, So there's no oncotic pressure pulling fluid into the alveoli. There's a rare disease called alveolar proteinosis. Now you know why it's such a bad disease. It puts oncotic pressure into the alveolus. Normal person, no protein in the alveoli. No oncotic pressure in the alveoli. The proteins stay in the interstitial space and in the capillaries. And that keeps the alveoli dry. So there's a high osmotic force in the interstitial space that any fluid that gets out of the capillary should be kept in the interstitial space, and then those proteins go into the lymphatic system and take the fluid out of the interstitial space with it. The alveolus has to stay empty or you're going to drown. That's also known as drowning. So the alveolus stays empty. How do we keep the alveolus empty? Very tight junctions to keep the protein out. At the same time, plasma proteins that keep the oncotic pressure keep the plasma proteins and the osmotic pressure in the interstitium so that it sort of dehydrates the alveolus. Pulmonary edema is when you raise the hydrostatic pressure in the pulmonary capillaries so high that it overcomes the oncotic pressure in the interstitial space. The picture on the next slide. The pulmonary capillary. There's very little filtration. The little filtration that does occur should be picked up by oncotic pressure, should be picked up by oncotic pressure in the interstitial space. The little bit of fluid that does make it out of the capillary should be picked up by the oncotic pressure in the interstitial space and then brought into the lymphatics. So it doesn't ever make it. There should be nothing making it into the alveolus. The alveolus has to be staying empty. Now, when the hydrostatic pressure goes up in the pulmonary capillaries, such as in congestive heart failure, that ends up putting more fluid into the interstitial space than the oncotic pressure out there can remove. When you have pulmonary edema, it is because the left ventricle backs pressure up into the left atrium and to the pulmonary veins and capillaries, so that more fluid ends up in the interstitial space than can be absorbed by the oncotic pressure there. And in pathology, fluid will end up in the alveolus. Fluid will end up in the alveolus. We give diuretics to decrease which of these pressures? Diuretics are given to decrease the hydrostatic pressure in the capillary. We give diuretics to decrease the hydrostatic pressure in the pulmonary capillary. So the main thing that changes here is hydrostatic pressures in the pulmonary capillary. When they go up too high, congestive failure. When they go lower, no congestive failure. Now this is also why low albumin states can give you some edema in here. Why would a low albumin state give you edema in there? Because when you have a low albumin state, the oncotic pressure in this interstitial space there doesn't pull the fluid out of the alveolus. You want the little oncotic pressure in the interstitial space to keep those alveoli nice and dry. If you lower your plasma proteins, you can decrease the proteins in the interstitial space. And if you decrease the proteins in the interstitial space too much, sometimes you can get edema in there in the lungs. No bueno. Now, Cardiogenic pulmonary edema is the same thing as left ventricle not working. If the left ventricle doesn't work, you get pulmonary edema. You get pressure that goes backwards into the atrium, backwards into the veins, backwards into the capillaries, and what ends up happening is that the lymphatic flow will take the proteins out of there, but after a while it's overcome and you start getting fluids going into the alveoli. Dyspnea is a $5 word for shortness of breath. You're short of breath because you can't oxygenate. You can't oxygenate because the alveoli become filled with fluid. See this thing here? Lower plasma proteins predisposed to cardiogenic pulmonary edema. Lower plasma proteins. Why? Because those plasma proteins help contribute to taking the fluid out of the alveoli and into the interstitium and draining it into the lymphatics. So oncotic pressure can actually help take fluid out of the alveoli. The wedge pressure is the same thing as saying the left atrial pressure. That's what wedge pressure is. Wedge pressure, which is a little hard to get into right now, is using a catheter into the right side of the heart. It's hard to figure out without visualization. But a wedge pressure is using a right heart catheter to measure left atrial pressure. You get a catheter, you jam it all the way into the pulmonary artery, you put a balloon up so that it blocks what's coming from behind it, and you're measuring just what's in front. And what's in front? Left atrium. Wedge pressure is the same thing as saying left atrial pressure. Wedge up is the same thing as saying I'm going to have pulmonary edema. Wedge down is the same thing as saying no pulmonary edema. Wedge pressure is left atrial pressure. When the left atrial pressure goes up, it puts back pressure back into the lungs. It increases the hydrostatic pressure inside the pulmonary capillaries. Om Namah hydrostatic pressure, and you get pulmonary edema. Decreasing the wedge pressure, diuretics. Decreases hydrostatic pressure in the capillaries. Sitting upright improves it because when you sit upright, you're taking pressure off of the capillaries in the lungs. If I'm hanging out upside down like this, I have more volume in my lungs. If I stand upright like this, it takes the volume literally out of the lungs. Diuretics empty the lungs. Non-cardiogenic pulmonary edema means that it's not from hydrostatic pressure. Non-cardiogenic pulmonary edema means I burnt the lungs, I inflamed the lungs, I fried the lungs. And it's not hydrostatic pressure that's driving it. Cardiogenic equals hydrostatic pressure. Cardiogenic means left atrial pressure, means hydrostatic pressure, means left wedge pressure. Cardiogenic pulmonary edema, let's say the thing in 5 different ways just to confuse the crap out of you. Cardiogenic pulmonary edema means left ventricle doesn't work, means left atrial pressure is high, means wedge pressure is high, it means pulmonary venous pressure is high, it means that pulmonary capillary hydrostatic pressure is high. That all means cardiogenic. Non-cardiogenic is this. Here we have blood vessels, and here's the alveolus. ARDS, sepsis, burns, fry the lungs. ARDS, you damage the capillaries. And you don't need pressure because you broke the walls, you damaged the walls, the fluid just leaks across. Fluid just leaks across, like Berlin Wall in 1989. Just leaks across, just leaks across. ARDS means that the lung, she's sick and I don't know why. Diffuse inflammation of the lungs for unknown reasons. Nobody knows what causes ARDS. Sepsis, burns, amniotic fluid embolus. It's many of the things that would cause DIC actually, ARDS. And the same way, we don't really understand what activates the clotting cascade to start disseminated intravascular coagulation. We don't understand what causes ARDS. People have tried to figure out for a long time. The steroids don't help. Steroids don't help. You correct the underlying cause and you hope. But steroids don't help. It's not that type of inflammation. Same way steroids don't help if I burn myself. But it's inflammation. Yeah, but steroids don't help. But it's inflammation. Yeah, but steroids don't help. It's a burn. It's fried. I can't put steroids on a fried chicken. Doesn't make it better. Non-cardiogenic pulmonary edema means the tissue, the cells have been burned, they've been damaged, they've been inflamed, they've just been damaged and they're leaky. So you simply see that it looks like congestive failure, but the wedge is normal. It looks like congestive failure, but the wedge pressure is normal. You lose epithelial cell integrity. That means the epithelial cells are damaged. It looks like pulmonary edema, but you have a normal wedge pressure, normal left atrial pressure, normal left ventricular pressure. It looks like pulmonary edema, but the pressures are normal. ARDS. By the way, that's the definition of ARDS. Chest x-ray looks like pulmonary edema, but the pressures are all normal. You have survived edema and fluid distribution. What this means is, ready? The major concept is to understand osmotic draw. If you have osmolality of 300, 300 in the cells, 300 outside the cells, nothing moves. If I give hypotonic solutions, what's going to happen is I'm going to lower the osmolality in the blood vessels, and the fluid's going to shift into the cells. If I give hypertonic solution, the fluid will move out of the cells. If I put red cells in a cup of water, the red cells will swell and burst. If I give you hypertonic solutions like mannitol or hypertonic saline, the fluid will come out of the cells and into the vascular space. So you've got to know those pictures. You got to know those pictures where you're looking at the intracellular fluid and you're looking at the extracellular fluid. And you got to know those pictures where it says, oh, it goes up, down, left, right. Well, there's only 3 or 4 of them. There's only 3 or 4 of them. You'll get it. You'll get it. You've got to understand that the Starling forces, looking at what favors filtration and what opposes filtration. Remember that what is for filtration is the hydrostatic pressure in the capillary and the oncotic pressure in the interstitial fluid or interstitial space. The flow means if your hydrostatic pressure goes up, fluid flows out. If your oncotic pressure in the interstitial space goes up, the fluid flows out. Now, if the opposite is true, the forces against filtration, the hydrostatic pressure in the interstitial space, interstitial fluid, and the oncotic pressure in the capillary, if the forces against filtration are more, that's called reabsorption. And you reabsorb fluids. Well, neither filtration nor reabsorption is by itself saying good, bad. If I have edema in my arm, having forces against filtration is a good thing. If I have an edematous arm, reabsorption is good. So is reabsorption better or worse than filtration? Depends what you got. Depends what you got. Okay? Depends what you got. Now, that's the very basis of pulmonary edema. You can't understand pulmonary edema without understanding that, because pulmonary edema is based on the hydrostatic pressure inside the capillary going up. On the other hand, ARDS, aspiration, sepsis, burning the lungs, inflaming the lungs. The capillaries are just leaky and damaged, and fluid just marches across. Doesn't need hydrostatic pressure because the epithelium stops being a boundary. The epithelium just stops being a boundary. So you'll see also that this concept of osmolar forces for and against is not that hard, except when occasionally they give you a calculation. And as long as you understand these two things, hydrostatic pressure and oncotic pressure, which is plasma proteins should not be filtering anywhere. They should stay where they are. The ones outside the vasculature should stay outside. The ones in the vasculature should stay inside. Remember, that's not saying lymphatics. And lymphatics are very loose, and proteins can go across. Lymphatics are loose, but capillaries are not too loose. Liquids can go across. Solutes like sodium, potassium, chloride can go across, but albumin should not be going across too much. Now, proteins can go into the lymphatics, and that's a good thing too, because that's how we keep the interstitial space cleaned up. That's how we keep the interstitial space cleans up, because the proteins can go into the lymphatics. That's also how we keep our lungs clean and dry. The lymphatics are there to pick up some proteins and to take all the fluid with it. So we keep our lungs nice and clean and dry. So what you see in this chapter is that there's not that many concepts, but they're indispensable concepts. It's not that many concepts to say osmolality, moving fluid in and out of cells and across membranes. But the concept of understanding osmolar draws is indispensable. The concept of understanding hydrostatic pressures, pushing fluids in and out of capillaries, is indispensable, and the same as oncotic pressures. You can't understand any of nephrology without getting this one. So what you'll see is that it hit it twice. Look, some people are going to get this on the first time. They knew it before they got here. They did physiology in college twice. They did it again in medical school. Some of you may have to do it 3 times, and then you'll get it. You'll get it eventually. But don't be disturbed if you have to look at some of these tapes 3 or 4 times. That's just the way it is. So the point is that it's not going to change these physiologic concepts, and don't be whiny about having to look at it 3 or 4 times. You may have to do that. That's okay. Then you'll get it. Then you'll be done. You'll feel happy, okay? See you in the next section.